Hello everyone! Today I'll be introducing the vector department I'm working in. The vector department is located in the quantity building with another department called the scalar department. Scalars only worry about the magnitudes of quantities, while we vectors care about both magnitudes and directions. In this example of the flying helicopter, we see the length of the routes are the same, so the distances, which are scalars, are equal. The displacements, which are vectors, are not equal since the directions are different. Now, these are photos of my colleagues. Our names are made up of the letters of heads followed by the letters of tails, with an arrow placed above them to show that we have directions. We add a symbol of absolute value to indicate our magnitudes, which are always non-negative. These vectors have the same magnitude but exact opposite directions, so they are opposite vectors, that is, vector AB equals negative vector CD. Equal vectors have both the same magnitude and directions. They are considered the same vector. Any vector with the same or exact opposite directions are collinear or parallel vectors. We work together using different types of operations. One of them is scalar multiplication. We multiply a number to the vector to enlarge or reduce its magnitude, or even reverse its direction, but the results are always collinear vectors. For example, I can speed up, slow down, or even go backwards by doing scalar multiplication to my velocity. We do vector addition too. This fourth experiment shows that the sum of two vectors is the diagonal of the parallelogram formed by these two vectors placed tail to tail. Because subtracting a vector is the same as adding its opposite vector, the parallelogram law applies to vector subtraction too. Another operation is dot multiplication. Work is one example. As we know, work is the product of displacement and force on the direction. But here, force OQ is not along with displacement OP, so we must draw a right triangle to project it on vector OP. The result OR is the magnitude of OQ times cosine theta, so our work is eventually the magnitudes of OP and OQ multiplied together with cosine theta. Until now, we are discussing the geometric vectors. They appear in math and physics very often. In opposed to geometric vectors, algebraic vectors are considered with coordinate axes. Two perpendicular vectors can represent all vectors on this plane using scalar multiplication and vector addition to adjust the length and directions. The x and y they multiplied creates a unit set of coordinates for each vector. Based on these two vectors, we construct a coordinate to represent all vectors. Since equal vectors are essentially the same vector, we place each vector with its tail on the origin. We can use operations on coordinates too. We add up coordinates separately in vector addition. In scalar multiplication, we time the scalar to the coordinate respectively. Same applies for the three-dimensional space, only they have three axes, or four-dimensional with four axes, and so on. Because algebraic vectors are easy to calculate, they are applied in many fields. For instance, if biologists want the average measurement of two kinds of bird, they treat each feature as a variable to construct a multidimensional vector. They then add them up and have the sum to get the average measurement. And that's the end of the tour. Bye!